Okay, welcome everybody. My name is Krzysztof Sroka. I'm a lead Flutter developer at Callstack, software house in Poland. And I decided to make a talk on performance optimizations in Flutter. First of all, this might be a little bit confusing if you don't know anything about Flutter. But if you actually did one app, I guess you would know most of what's required for this talk. And I also did this talk because I couldn't find like one concise source of information on how to optimize Flutter apps. When you go through docs, this is scattered across many classes. And I'll try to combine most of the knowledge here. First of all, why do we even care about this? So when people say 60 FPS is a target they want to achieve, they sometimes say, well, I can actually achieve this kind of speeds of 60 FPS. And this is, of course, not true. The nerves in our eyes and in our brain can fire up to 1,000 times per second. So that's a long way from 60 to 1,000. So 60 is pretty low, and our eye, while it can fire, let's say, once every 1,000th of a second, the brain is pretty good at smoothing it all down. So the eye could actually detect like flashes happening at this frequency, but the brain doesn't really care. The brain can see like bright lights, but if we think about having smooth animations and everything happening slowly, but not let's say in a games, then 60 FPS is good, 120 FPS is very good, and I think above 120 FPS you actually need to write game apps that need lots of flashing lights to notice a difference. If you write a regular app, this the 120 FPS should be good for you and good for your users. And maybe in a couple of years, this talk could be renamed Fluttering at 120 FPS. So how does Flutter achieve the 60 FPS? I'll use 60 FPS for the remainder of the talk. It has several threads of execution, of course, and two important threads of execution in Flutter are the UI and GPU thread. And the first one runs our Dart code. So everything that's written in Dart in Flutter actually runs on that, not everything, but everything related to UI runs in that thread. And the other thread runs a Skia graphics engine and all the operations later on. And I'll focus on the framework part, because optimizing engine is totally not something you would do ever. So the Skia engine is really, really complex, and if you do optimize, you probably don't think about going that deep. However, some things, of course, affect how the Skia works, and I'll talk about them. So it's best if we actually have this kind of situation. So vsync. This is a timer that runs as quickly as our machine can do. So in 60 FPS diff plays, it will run every 16 milliseconds and twice as fast in 120 FPS, the displays. And when it fires, the framework starts working. So all the building of a widget starts over there. And once that's done, once the Dart code finishes execution, it ends up with a series of instructions to the engine, and engine follows immediately after that. So yeah, ideally, it would all fit, this one frame would all fit in 16 milliseconds. But it's also not that bad if it goes slightly slower, because the framework actually starts its work every 16 milliseconds. And if we complete before this time passes, it can start again. It doesn't wait for engine to complete its rendering. And the effect of that will be that we will see just a tiny bit of latency between, let's say, our inputs and what we see on a screen. So let's say in 16 milliseconds, but the refresh rate and frames per second will still be the same. Before I actually get to the optimization, it's really good to understand how this works a little bit deeper, how this works under the widgets. Because we've heard a lot of times like that everything's a widget in Flutter, that it's all widgets, and it's not, of course, true. There are other things other than widgets. It's all widgets should actually point to us that we can compose pretty much everything with everything else, and these are interchangeable parts. But the widgets translate to the second tree. We can think of it as a tree, translates to the tree of elements. The elements actually are the basic blocks and the most important blocks in the Flutter framework, because this is what Flutter uses to actually perform all the operations. It doesn't go that much into widgets themselves. It runs most of its functions on elements. And it's almost widgets and elements because it's also render objects. So there's a third tree called the render object tree. Render objects are not always, there's not one-to-one mapping of widgets to render objects or elements to render objects. Some of the elements map to render objects while others don't. So other objects, other elements are just passed through in this tree. Eventually, all the leaf nodes in that widgets or element trees will become render objects. And how does it look like in more detail? You don't need to actually remember all of this. It's just we have like 3 basic types of widgets, or 3 basic groups of widgets on the left-hand side. And these are called basically configurations. So this is how we configure Flutter to run. And first and second are what we usually use in Flutter as developers. These translate to subclasses of component element, which doesn't have an associated render object. While the third group, let's say, render object widgets, are frequent in Flutter SDK. So these translate to render object elements, and these actually do rendering. So whenever you write a widget that needs to change how the child renders, you write a render object widget. But usually you don't. You just compose what's there, and that becomes a component element. So I've described a little bit how the structure looks like, but how does it work? What happens during a lifetime of our application? And it's crucial to focus on this element part, because that's a basic building block for Flutter, which has this kind of life cycle. First, it gets mounted, so the first time it appears in a tree. Then it gets marked as needing build, or you frequently see it's being marked as dirty if you take a look at the logs. Then it's like an endless cycle of being rebuilt and being marked as needing build. So I'll soon explain how this ties to widgets itself. And there's an end of life for an element, which is being unmounted from a tree. Once an element is unmounted, you can no longer use it, and Flutter will try to scream at you if you do. So when the element gets marked as dirty, and let's say widgets also get marked as dirty together with the elements, this actually isn't a synchronous operation. It gets put on a queue of widgets to be rebuilt at the next vsync run. So at each vsync, the framework will pick up the queue of dirty elements and try to rebuild them to make them clean again. And this rebuild, in turn, we'll try to go to, let's start with the rebuild. Like if an element is marked as needing build, it will start with rebuilding. Then it will try to update its children And in this case, there are multiple children of an element, but Flutter usually, in Flutter, we will see that lots of elements and lots of widgets have basically one child. So there's like long stream of single child structure. But eventually, let's say if we rebuild our root application, all the leaf widgets and all the widgets on the way will need to be rebuilt, more or less, because there's more to that. So I'll show a little bit of optimizations of how Flutter itself does optimize this update step. It takes an element, an existing element that it mounted, and when we try to associate it with a new widget, or we update the widget actually, it will try to compare the element's association with the widget to the new thing. And if that's the same widget, so this happens when it's actually a const widget, it's compile time constant widget, and the configuration can never change, it will not touch it, and the update will actually finish here, not touching any of the children of that element, and that's the most optimal part. However, const widgets are not that frequent in our applications, and when they appear usually close to the bottom of a tree. The second thing that Flutter does is it tries to compare the type and the key of the old and the new widget. So if we reuse the same widget type, we just change something, like rebuild with a different parameter, or we call it a new constructor, different parameter, and we preserve the same key, or we don't have a key in between new and old widget, it will actually be able to update it as a regular flow. It's still going to pass down the update stream and rebuild stream down. There's also one other step. If we use global keys on our widgets, we put the global keys. They are basically unique across the whole app. And in some cases, we can use that to transfer the whole subtrees of our application from one place to another. I'll explain. This is a little bit too much of an optimization, and you can use that in some cases, but this is happening quite rarely, and you shouldn't abuse the global keys to put them all around your app. Now, if none of these conditions happen, there's like the worst case scenario. So Flutter will actually discard the element that it used previously and recreate the full subtree from this point on. This is not like crazily expensive, but it's most expensive of the operations that it can go through. Oh, and how does it tie to set state? So set state is this basic tool we use to actually rebuild widgets, right? And set state has usually this kind of form. We pass to the set state some void callback that's going to set our state variables. But unfortunately, it's a lie. So whatever we pass a callback doesn't really matter. It doesn't really tie to any state. And if you come from, let's say, React Native or other reactive frameworks where state is actually compared across widgets, you might think, well, I set my state variable and my widget didn't rebuild, or I didn't set any state variable and the widget did rebuild, and it shouldn't happen. Unfortunately, what set state does is this simple. It executes synchronously the callback you pass and marks the associated element as dirty. And there's no more magic to it. So basically, it doesn't matter what you pass in a callback. And I'll come back to it later. So now I'll go through some steps of how to optimize your Flutter application. With that knowledge, we'll know a little bit already how to make our application faster. First of all, we don't optimize. So there is no problem until there is one. Premature optimization is something we really like to avoid, especially like using constructs like global keys or rearranging our code just to be most optimal before the problem appears. We start optimizing when the problem appears in production release and not earlier. Some of these things can be applied. For example, as we could see, the const case is the most positive or fastest case of update. And linter can actually tell you to use const whenever possible. I do that, but it doesn't give lots of benefits. It's just, it does remind me, and I put const everywhere. It's not a huge issue. So other thing you shouldn't do refers to the second part there. You shouldn't reassign keys. Like keys should really tell you what is the widget underneath. You shouldn't, let's say, build a new key because a value of a widget changed. It should be like more semantic information of what happened. It could be a position on a list. And again, since Flutter has this really long structure of single children, keys don't really matter. If there's only one child, if you have the same key over time or no key over time, it's going to work. But you also cannot change the types in that tree. And one common mistake is, for example, using offstage or visibility widget conditionally, like putting them inside of a tree only when they are used. Most of these widgets have now flags enabling and disabling them, so that you shouldn't actually change the structure of a tree, like removing these widgets when you say, okay, now I'm not off stage, or now I'm visible. You should just use a flag, and that preserves the structure of the tree, and it's, the tree doesn't need to get recreated. Yeah, and the final thing is global keys are useful. Global keys are sometimes useful, and I recommend using global keys only in like big subtrees. Let's say you have a screen, but for whatever reason you need to move around the tree. Like sometimes it's attached to one widget, sometimes it's attached to another widget, and you cannot work around this. Use a global key then, because otherwise it might just be very expensive to rebuild the whole big subtree. For smaller elements, somewhere closer to the leaf nodes, it wouldn't really matter at all. Okay, so these were like basic optimizations we could deduct from how the update works. And I'll go through some of the practices, but also, of course, tied to how these updates work, but are maybe more applicable in day-to-day life. So one thing is set state. It's a very basic operation we use every day in Flutter. And set state, unfortunately, has this effect that once we set state somewhere in a tree, it's most likely to propagate down, and the whole subtree will be recreated. So one thing you obviously can do is pushing the set state closer to the leaf nodes, so that it doesn't affect the huge portions of a tree. And the other thing is that you shouldn't really fire set state frequently. Like if you have a large widget with a large subtree, try to minimize the number of set state runs. One common mistake people do, and this is especially in animations, is to have set states run over time. Let's say it's most frequently tied to animation controller, where you just add listener, and the listener calls set state unconditionally. In many cases, we can predict where something will change, and on a screen after our animation. And we have sometimes this pattern, like we set state, and inside of a callback we have a condition And of course, this pattern ties to what I said before. This is a mistake we make when we think, oh, it's actual assignment of my variable that matters, but it doesn't. So if you have a pattern like this, try to switch it like this. So first test whether the condition happens, whether you need to update your widgets, and then call setState only afterwards. What's also possible if you, for example, want to preserve the value. Well, for example, here, if there's a new shiny value, we wouldn't preserve it at all. We would just drop it and not update our internal state. We can do things like this. We can set variable always, and then only if condition happens, if a condition is satisfied, we set state. However, there's a warning. This, in complex widgets where you have multiple places where you fire set state, can be very confusing. Because you will have cycles where you update your variables, your class fields, and not fire set state. And in another place, you fire set state without updating them, and you'll be very confused what happened and why things have changed. So that's one of the things, like how to limit the number of times that set state happens. How to limit the changes affected by the state? Well, we get rid of set state on a very top level, and instead we can use basic blocks like inherited widgets. Inherited widgets are there to provide data, basically pass the data we know about in a bigger scope down to the specific widgets downstream. And one nice thing is that if we are somewhere down the stream, down the tree in our structure, asking to find an inherited widget is actually based on a hash map. It doesn't, getting data from an inherited widget doesn't need to traverse the tree up. The context keeps the hash map of inherited widget types to the instances, and this is quite easy to, even if the distance between inherited widget and the widget that uses its data is big, it's as fast as if it would be a direct child. One thing we'll need to actually say also by inherited widgets is it's not fire and forget. If you have a big model in your inherited widget, like the data you keep actually is composed of several segments. We then made fire too much. So we notify, the inherited widget always notifies all of the descendants, all of the widgets that depend on it every time it updates. And if you have segments of data in your inherited widget, actually it's here, you might fire unnecessarily. So notify widgets to rebuild, even though the data they depend on doesn't really do that. So the two things you can do to prevent this unnecessary updates is first to split inherited widgets into multiple parts. So add multiple inherited widgets in your tree, but it only works for like several and let's say known number of items. Otherwise, if we have a large data set, let's say a table or a grid, and we want to provide each item from that grid or table to widgets separately, we can use inherited model, which actually allows us to do that. So the widgets tell the inherited model, hey, I want this part of the data, and they won't be notified if another part of the data is being changed. Okay. One other easy thing to fix is that try not to split widgets too much. If you have like a padding in all the cases, this would be a really bad thing to do. To have a separate padding widgets for left, right, top, and bottom, because all of them create a new render object, and each of these render objects separately tells Skia to offset your widget by some amount. So use common shortcuts for having this in one widget if it's feasible. However, there's also caveat, like there's this nice widget called container, and container has several options like padding, decoration, and so on. Unfortunately, it doesn't work this way. It just internally nests the widget it needs and puts them into tree altogether. So there's no actual benefit from using container in this case. Now, one other thing that's common is that doing heavy lifting in a UI thread. So imagine we have a build method, and suddenly because of URL change, we try to fetch some data and process it in a build function. We would like not to do that on a UI thread, since it's going to basically slow down the rendering for the whole part of the application. And what we can do is use compute method. So compute method will actually start our task in a separate thread, forking from the UI thread, and it is going to return a future result once it's, of course, complete. But it's not going to block the UI thread, and it gives us opportunity to render faster. And now a little bit more about detail about actual render objects. So this is a render object tree. It has several of the nodes, and when render objects represent actual parts of the graphical parts of the application, right? Imagine we have the yellow object marked here is a small circular progress indicator. It always has the same size, it doesn't change, and the application doesn't need to be updated whenever this progress indicator spins. So the rest shouldn't really, the rest of the application shouldn't really react to that. Unfortunately, by default, when we do a change like this in a leaf node, it will actually try to propagate up to the parent, that is a repaint boundary, possibly up to the root of your application, and then when it finds this ancestor in your tree, it's going to propagate everything down. So eventually, the whole of your application might repaint just because you changed a small part of your UI. This is especially important if you have some animation, as I said, or maybe a view that updates independently of the rest of the application. This is, of course, a different scenario than when you actually change the layout of elements, so they need to render differently. But in this scenario that it's just the paint itself changes, we can introduce repaint boundaries. And repaint boundaries guard us both for propagating up the tree. As you can see, only the subtree on the right actually got marked in yellow, which means it's marked for being repainted. And also, it stops propagating down. So this one small widget in the middle of that subtree also wouldn't be repainted if the parent just repaints its children. Of course, as I said here, if layout changes, this doesn't matter. So this is something that can be used if you have heavy widgets, but they don't change in size, they don't change much of a position. So these layout constraints are the same. And also one final touch, like don't use this. There are different clipping modes when we speak about composing different render objects. And some of these clipping modes are expressed through parameters in our widgets, in material widgets. And this option is one of the options available to you. it's going to make your UI look really smooth. Like if you have one widget on top of the other with some fading in, fading out, and borders around this, this is going to be very, very nice looking. But however, if you use it in animations, it's basically going to make your GPU burn. If you use it in like some, I did test it on my toy app, and it required me just to have 5 widgets with a small animation like opacity and just a single number within each other. But 5 of these widgets on a not so modern but not so old Samsung device made the application basically stop and refresh every half a second. So use this option sparingly. It's also, I mentioned here also because this is easy to overlook. You don't do much. It's just a single parameter to one of your widgets, and suddenly your application might get so slow it's unbearable. Now, your app is slow. What do you do? How to get help in this case? First of all, by default, we run our applications in debug mode, and debug mode has lots of calls that are not necessary in release. So there are actually 3 modes that we can run our application in. One is, of course, debug, the default. One is release, when you try to distribute an APK or on iOS, other file. Sorry, I'm not the iOS developer. And there's a profile mode, which is basically a release mode, but it allows us to gather profile data. And I'll soon show you how this profile data looks like. So before we actually go and try to fix problem, we need to verify that this happens in a profile mode. Some problems only show up in debug mode, which is, I would say, not the greatest developer experience because you know the problem isn't really there. It's just that the Dart VM adds an additional steps and makes your default mode, the development mode, slower. So I would recommend using some placeholders instead of your widgets that are really slowing you down in debug, because nobody wants to have a slow debug mode and fast reload. Basic tools, the performance overlay. This I actually made a mistake in this slide. So performance overlay is a simple widget that draws on top of our app. As you can see, this is like a default app that we get when we do Flutter create. And I'll show you how it looks like, because there's a video. So this performance overlay shows us 2 graphs. The top graph is the graph of a GPU thread. The bottom is of a UI thread where our Flutter code, Dart code runs. And you can see here, I need to restart this. You can see here like the progress bar going from left to right. It's mostly green, but when it's red, it means we crossed the 16 milliseconds boundary. And this only happens, or this only gets any progress, of course, when there is an update to the state. So when I actually pressed the button here, and this is like a most simple tool to let you know, hey, where the problem might be, what user actions trigger the problem. But it's very basic, and there are more advanced things. So. And use it in, as I said before, in a profile mode. I used it here in debug mode. You can see the banner over there, just to show that there can be red bars. Otherwise, it would be very smooth. The other thing is that if we confirm our problem that we have, what we see in debug mode is actually there in release, we can go back to the debug mode and try to see what happens with our app. And there are multiple flags like these that allow us to inspect why the widget is getting rebuilt or why the element is being marked as dirty, when the frame starts and when it ends. Maybe there are multiple operations that go inside one frame that shouldn't be there. And there's plenty of them. I guess some of them, either from community or from you, could actually write a blog post describing all of them, but it's really, really lots of them. And they are scattered all over the place. But usually they start with the debug print. And one of the neat flags is debug repaint rainbow enabled. So repaint rainbow gives us nice visual overview of what gets repainted. And you can see, I don't know how much visible it is. Whenever a widget updates, the border around it is going to change color. So this is a rainbow color. It just progresses through the colors of rainbow so that you can have a visual hint what gets repainted. So that's another maybe not very advanced tool, but if you, for example, don't expect something to be repainted and it does, like a widget that doesn't even change its appearance, there's something, it can give you an idea, hey, this might be a source of a problem. Now, this is the most advanced step, I think. So if you couldn't figure out what's going on, like all these flags and these tools weren't enough, go for the profiler, actually, and timeline debugging. So when you run your application, you sometimes see this line, an observatory debugger and profiler is available at this address. So this is not the best of UX experience, actually. This observatory looks like it was written a long, long time ago. But there's also a view called the timeline. It's only available in the profile mode. Otherwise, it will say, well, there's no profile data for this. And it displays you this crude, well, but more useful if you would like to dig in, series of charts, actually, where you can dig into what specific operation took how long. So on the top, we have actually our application lifetime. And we can see here, these are frames on the left-hand side with a bluish background. There is some flashing of tasks. The vsync, actually, before it hits, there's some scheduling overhead, so it prepares to be run. Okay, and then actually, we flash tasks. That means we run over timers. One of the timers is vsync, this begins frame, this introduces some frame workload, and in the end, it drills down to build, layout, paint, and below you would see even like more specific parts of the application, like what gets called, which paint, which build, which layout. But it's not that easy to use as well. However, one nice thing about this is that you can add your own elements to this timeline, and in this way, you can basically check if what you do synchronously, of course, you need to do it synchronously. Asynchronous operations, you don't test like this. To show up on this timeline, and you can actually visually see, hey, how long did it take? This timeline actually exports to data through the Chrome debugger compatible format. It's like JSON, I think, with some Chrome debugging formats. And you can read it in other tools, maybe with a better UI, that allow you to do this. And yeah, I think that's it. So I went through lots of things here, and I'm happy to chat with you afterwards if you have more specific questions. I'm almost done with time, but I guess we can take a couple of questions now. Yeah, and that's my, if you want to reach me, my Twitter handle is that. And I work at Callstack. You can visit us at callstack.com/flutter or write at flutter@callstack.com. So, thank you. Any questions?